I'm Cammy.
And I'm Hannah.
And this is our hybridization project.
We hope you enjoy.
So what is hybridization? Hybridization explains the bonding in molecules that don't fit into the valence bond theory. It says that the central atom makes new orbitals before it bonds with another atom. These new orbitals that are formed are called hybrid orbitals and are formed by combining the atom's atomic s, p, and d orbitals. The orbitals that combine together must all come from the same energy level. Remember, for each hybrid orbital needed, you must use one atomic orbital.
Now let's hybridize phosphate. Step 1. Draw the complete Lewis diagram for the molecule. Use the have-need method to determine how many bonds are in your molecule. First, we draw out the molecule. We start with the central atom and fill in the surrounding oxygen atoms. Then begin the have-need method. We have 5 valence electrons for phosphorus, 6 valence electrons for oxygen 4 times, and an extra 3 because the charge of phosphate is -3. This leaves us with 32 electrons. Each atom needs 8 electrons to be satisfied, so we do 5 times 8, which is 40. Then we do 40 subtracted by 32 divided by 2, which is going to give us 4 bonds. Then we fill in our valence electrons and bonds and complete the diagram with a charge.
Step 2 is to write out the condensed energy electron configuration for the central atom. In this case, it's phosphorus. So we take out our periodic table, we look for phosphorus, and then look for the closest noble gas, which is neon in this case. Then we count our orbitals, 3s2 and 3p3. So now we write it out. We have neon, 3s2, 3p3. But we can't forget about the charge of phosphate, which is -3. So we must add 3 to our p orbital. So our final answer is going to be neon, 3s2, 3p6.
Step 3. Draw the condensed energy level diagram based on the electron configuration. Start out by making the graph. Label the y-axis potential energy, or PE for short, and have the x-axis as our S and P groups. Start out by writing neon. Then we move to the next orbital, which is 3s2, and we write down 2 electrons and label it 3s. Then we've got our p orbitals, and we have 6 electrons, and we label that 3p.
Now, let's take a moment to gain an understanding of intramolecular forces and tie this back to our previous knowledge from years prior. Intramolecular forces are the bonds that are in a single molecule. They can either be covalent or ionic bonds. In phosphate's case, we have polar covalent bonds. We can determine this by calculating phosphate's electronegativity, or En. This number, once calculated, lies between 0.4 and 1.7. Step 4 and is to therefore, hybridize. Phosphate has to do polar this, covalent we look bonds. back at the Lewis dot structure, count the electron groups, and determine the types of bonds that they are. Draw an arrow with the word hybridization on top and the kinds of bonds below to symbolize the arrow of the hybridization process. Looking at phosphate structure, we can see that there are 4 electron groups. 1, 2, 3, and 4. So now we must recognize the bond type. With them all being single bonds, in a hybridized molecule, these bonds are either sigma or coordinate covalent bonds. In this case, since the Lewis dot structure of oxygen atoms are the same with calculated with the half-need method, or by itself, and on the phosphate structure itself, both of these numbers being 6. This means that the bonds are coordinate covalent bonds. Now we take out a ruler and draw an arrow. Hybridization goes on top again to symbolize the process that the electron is undergoing. And on the bottom, 4, and then our type of bond, which is a coordinate covalent bond.
Step 5. Draw a new energy level diagram with the hybrid orbitals taken from the atomic orbitals in the original diagram. Fill in the electrons just as you would with a regular energy level diagram. Then write the final name for the hybridized orbitals. In order to draw the new line of orbitals, you need to average them out and put them in between the two existing ones. Then you will use the electrons to fill in the orbitals. In order to name it, you combine 3s and 3p and make 3sp3. The exponent on the 3 stands for the 3 orbitals used from the p section in the first graph. This is the final product for hybridizing phosphate on an energy level diagram.
When we talk about bonding in hybrid orbitals, these are the type of bonds that can be found. Sigma bonds, lone pairs, and coordinate covalent bonds. Pi bonds do not have hybrid orbitals as they are formed using regular atomic p orbitals and only have one electron. Phosphate has polar covalent bonds, which is a subsector of coordinate covalent bonds. In terms of resonance structures, phosphate does not have one. Since phosphate structure looks like this and does not have a double bond or does not rotate like sulfate, it is not a resonance structure. If we look at sulfate, we can tell the difference. Covalent bonds, or if it has sigma bonds, we look at the oxygen atom. Since the oxygen atom has 6 valence electrons on its actual Lewis dot and on the Lewis dot of the molecule, that means that we have coordinate covalent bonds in the molecule. If this number was different from the number in the molecule, i.e. we had a double bond somewhere like this, and then 2 of the oxygens would be eliminated, then it would be a sigma bond. Therefore, phosphate only has 4 coordinate covalent bonds.
Here are 2 physical properties of phosphate. Phosphate has polar covalent bonds, and therefore one of its physical properties would be that it can conduct electricity when in a solution, as it forms the ion with a -3 charge. Another physical property is that it has a higher boiling point than nonpolar compounds, as it has a higher attraction between the atoms in the molecule due to their differences in electronegativity.
And that concludes our presentation. Thanks for watching. Hope you learned something new.